energy of the wind be put to use? In other words, how does the wind turn the rotor of a windmill or wind turbine? Wind turbines may be used to pump subterranean water to the Earth's surface or to turn an electricity generator. But discussing the different ways in which wind energy can be exploited is not the main aim here. Let us simply go into the principles that make a wind turbine work. In addition, to simplify matters, only horizontal axis windmills, and not the numerous other types of windmill that exist, will be dealt with.
Now, if a relatively lightweight rectangular surface is inserted into an airstream, this surface will be displaced in a direction at right angles to its position. This, of course, does not take into account other factors, like gravity and various frictional forces. What exactly is happening here? The movement can be interpreted as the result, or the resultant of two forces, one that exerts effort in the same direction as the airflow, known as drag, the other, which is at right angles to the airflow, known as lift. Now replace airflow by wind and attach one end of the flat surface to an axis that lies parallel to wind direction. In other words, the surface is now part of a rotor. Plainly, the rotor blade cannot move with the drag because it is held fast at one end. The lifting force, however, can cause the blade to move and, as a result, it becomes a propelling force. This force may draw the blade around its axis in a rotational movement, as long as it remains superior to gravity and friction. Obviously, some means must be utilized to maintain the rotor blade's equilibrium. For example, a counterweight may be fixed to the axis on the opposite side of the rotor. But most wind turbines are equipped with at least two identical blades. With two blades, a coupling effect is produced. That is, a pair of symmetrical and parallel forces acting in opposite directions. As a result, the rotor rotates. Other types of coupling effect involve the use of several rotor blades placed equidistant to each other around the axis. The strength of the force acting on the rotor varies according to the angle between the blades and the wind. This angle is known as the angle of incidence. Wind tunnel experiments have shown that the best angle of incidence is around 38 degrees. When extracting power from the wind, however, rotational speed is the most important factor. This depends on lift, which should be at its optimal maximum, with respect to the drag, which should be at its minimum. In practice, it has been shown that angles of around 10 degrees give the best lift-drag ratio. Optimal lift, however, is not the only important factor in the story. A regular rotational speed may be more appropriate depending on the use the wind power will be put to. This means that various techniques may be brought into play to take wind variation into account. One is to adjust the angle of incidence between the rotor blades and the wind. Wind turbine engineers talk about adjusting the pitch. That is to say, the angle between the blades and the disc swept out by rotation. But adjusting the pitch implies adjusting the angle of incidence. Now, as soon as the rotor starts to turn, things become somewhat more complicated. For the sake of simplification, imagine that wind direction is constant. The blades slice through the airflow in such a way that they intercept it obliquely. The change in direction resulting from this effect with respect to the true wind direction is known as apparent wind. Rotation creates a new environment in which the various forces involved must be re-examined. Apparent wind generates lift and drag, and hence the direction of blade movement which results from them. Seen from another point of view, the movement is a result of two aerodynamic forces acting in combination on the aerofoil. One which has no power to act due to the fact that the blades are held fast by the central axis, and another which, in effect, causes rotation. Bearing in mind that speed of rotation determines the difference between true wind speed and apparent wind speed, and that this increases as the distance from the center becomes greater. Some wind turbine blades have a built-in twist. This means that the pitch has been pre-adjusted along the length of the blade in accordance with expected apparent wind. Of course, blade pitch is just one example of the parameters which have to be dealt with. Here are some more. Firstly, it became clear that the flat sails used on the windmill rotors of bygone days were less efficient than blades with a cambered cross-section. The camber increases the lift-drag ratio by causing a low-pressure zone on the curved side of the blade. As a result, the blade is sucked into this partial vacuum. Nowadays, aerofoils similar to those found on aircraft and whose characteristics may be studied in wind tunnels are used. Secondly, if the width of the blade contributes nothing to output of the rotor once it has started to turn, for an equivalent wind force, width is directly proportional to lift during startup. Thirdly, during the initial effort of startup, lift is related to the number of blades in the rotor, but as the rotor gathers speed, it eventually behaves as a solid disc positioned side-on to the wind. In other words, the wind tends to flow around the obstacle rather than through it, preventing a further gain of power. So, when optimal wind energy extraction is the main goal, multi-bladed rotors are excluded. Fourthly, the length of the blade is important. The longer the blade, the greater the disc area, since the blade is its radius. Increase the disc area, and the chances are that power extraction will increase too, but there are obvious limits related to weight and cost. Finally, rotational speed, and in particular the ratio between blade end speed and real wind speed, are a reflection of optimal output. The faster the rotation, the greater the output. But speed itself, because of factors such as centrifugal force and vibration, cannot exceed specified limits.
These examples show how the engineer is confronted not only with factors inherent to the principles of aerodynamics, but also with a series of parameters which are directly linked to the task that the windmill is destined to perform.